All right, this is the third part and the last part of Simple Regression Model, Chapter 2 of the Wooldridge textbook. So far we have talked about what is simple regression, and then we talked about how OLS is doing the job, calculating the coefficients, beta hat 0, beta hat 1. And then we talked about the properties of beta hat 0, beta hat 1, like expected value, variance, and we at least talked about the shape of the distribution. And we said why we need to have those Gauss-Markov assumptions. There were 5 assumptions that we already talked about. And in this class, we're going to quickly review those assumptions and specifically focus on the last one, the homoscedasticity. And we are going to see why we need homoscedasticity assumption. And after that, we are going to implement everything in R. All right, so let's begin. So quickly reviewing the assumptions, remember assumption number 1, we need to have linearity in parameters. We said that the model needs to be linear in parameters. And then assumption number 2 was our simple random sampling stuff. You know, because without random sampling, then there's a good chance that our estimates are going to be biased. There's not much you can do for this course at least on this step, because you're given the data sets. And most of the time in real world, when you're doing a project at work, the data set is going to be given. You don't have any power in terms of making sure that the sampling has been done randomly. Okay, so that's a job for surveyors or statisticians. Then assumption number 3, we said that we need to have the variance of x to be at least some number greater than 0, because without the variability in x, we saw that OLS is going to have a hard time pinning down the slope and the intercept. And then we talked about the zero conditional mean assumption. So on average, the expected value of unobserved factor should be independent, mean independent of the explanatory variables. And I just want to emphasize one more thing here. Remember, if I have something like this, I can conclude that the covariance between, or correlation, doesn't matter, x and u is equal to what? Is equal to 0, right? Because remember, strong independence will lead to mean independence, and that will lead to correlation or covariance equal to 0. So when we have this assumption, zero conditional mean assumption, automatically we get this one. Covariance between x and u is equal to 0. All right. Then we said that, okay, based on these 4 assumptions, what can we do? There was a theorem, and that was the unbiasedness of OLS. We said having these 4 assumptions, we are sure that the OLS coefficients are on average hitting at the target. So the expected value of beta hat 1 is going to be exactly equal to beta 1, which is unobservable. However, the beta hat 1, I can see one of these beta hat 1s because I work with only one sample. So, but if I keep doing that sampling many times using some mathematical properties, we can prove that on average we are hitting at the target. What is the target? Population parameter. All right. Then we talked about interpretation of the unbiasedness. This is very important. Every single bullet point has a it's very important, and there's a good chance that you will see them on the exam. So the first one, we said that the estimated coefficients may be smaller or larger depending on the sample that is the result of the random draw. So it basically says that the beta hat that you are calculating from one sample that you're given, there's a good chance it can be greater or smaller than the beta 1, your target variable. Remember, on average, they're equal to each other. On the expected value, beta hat 1 is equal to beta 1. But for any specific sample, we have no idea. That's number 1. Then, so we focus on this on average term. So we said on average, they will be equal to the value of the character. So on average, they're equal to your target variable or population parameter. And then we said, what does this on average mean? On average means that if you keep doing this random sampling many times, it's a concept for a repeated sample. And then finally, so this is very related to bullet number 1. So that in a given sample, so these numbers, these estimates, beta hat 1s, beta hat 0s, may differ considerably from the true values, beta 1 or beta 0. We can never know for sure if they are whether this is the case or not, whether this is greater or smaller. Okay, so this is very subtle. Make sure you understand this very completely. All right, now then we talked about homoscedasticity. We said, you know, the variance for this is homoscedasticity has something to do with the conditional variance. Conditional variance of u given x is constant. So it means that if this is my y, this is my x. If I look at the variance for different level of x, variance of y given x for different value of x. So these are variance of y given x. For any different values of x, it seems that, well, maybe my right. The point is that the distribution is very the same for any. So the variance, if you look at the variance is constant. So the variance of y given x is constant. But wait a minute, you said that we need to say something about the variance of u given x, not the variance of y given x. Well, mathematically we can prove that they're the same. So here's an exercise for you. I want you to show that the variance of y given x is equal to the variance of u given x. And as a reminder, I never ask you to do these kind of proofs on the exam or homework, but this is just some kind of food for your thoughts. Think about it, why this is the case, and I'm going to prove it in the class. Why? All right. And so how do we interpret it in simple English? The value of the explanatory variable must contain no information. So x must contain no information about the variability of the unobserved factors. All right, then we stopped here. So this is a new thing. So the slide number 6 is a new thing. And so why do we need to add assumption number 5? Because remember, having the first 4 assumptions, I can say something about the unbiasedness of OLS. For unbiasedness of OLS, I didn't need to say anything about the homoscedasticity. I didn't need to make any assumption about the variance. However, I went ahead and regardless, I made that assumption. I made the assumption of homoscedasticity. So why do we need to make this assumption? The reason is that you want to say something about, you want to quantify the variance of beta hat I, or let's say 1. Right? So let me quickly write it here. Simple linear regression assumption number 1, assumption number 2, assumption number 3. This is important, assumption number 4. With the first 4 assumptions, I said OLS estimates are unbiased. It means that expected value of beta hat 1 is equal to beta 1. Expected value of beta hat 0 is also equal to beta 0. But again, in simple regression, we really don't care about beta hat 0. It doesn't. We cannot interpret that. It doesn't make any sense. And assumption number 5, homoscedasticity thing that you're adding. So you're adding it because with these, oops. Now that I have these 5 assumptions, I can I can come up with a functional form, a specific functional form for the variance of beta hat 1. And we do care about the variance of beta hat 1. Why? Because at the end of the day, remember, we are, if this is my population, we are dealing with different lines. For each sample, we get one of these lines, right? And we hope that the variance of these lines, the variance of the slope, is small. The smaller the variance is, it means that we are getting closer and closer to that unobserved population the regression function, right? So that's important. I want, you know, if it is small, we are happy. All right. Now, we say under assumption number 1 through 5, so this is what I just showed you in the previous slide. If I have the first 5 assumptions, then I can mathematically show that, prove that there's a functional form for variance of beta hat 1. And this variance of beta hat 1, again, we can come up with the variance of beta hat 0, but this is really not important because we don't pay too much attention to the slope in the simple regression. But this is super, super important. So important. I want you to understand it very deeply. Okay, so let's open up this equation and see what do we have. So let me write it down here one more time. So the variance of beta hat 1. It says that the variance depends on multiple things. The first, it depends on sigma square. Okay, So I'm gonna complete it and complete this equation as we move on. So the first one is sigma square. Remember, what is sigma square? Sigma square is the variability of the unobserved factor, right? So we want to see if the unobserved factors are very, very variable, then the variance of beta hat 1 is going to increase. So if this number is high, the variance of beta hat 1 is going to be high as well. Why do you think that's the case? What does it mean if the sigma square is higher? What does it mean? It means that the data is noisier, right? You are putting lots of things in that unobserved factor, and that unobserved factor itself is going up and down, it's jumping up and down a lot. It's very variable, and if that's the case, if the data is noisy, so OLS is going to have hard time pinning down the beta hat 1. What does that having hard time mean? It means that the variance is large, right? So going back to this slide, so this is if the data is all around the place, then the OLS is going to have hard time pinning down these lines. So that's the intuition. Number one. It depends on some other thing as well. So what's the second one? The variation in explanatory variable variance of x, or we can ignore the sample size and call it SSTX. So let me write it down. So summation of xi minus x bar 2. So why here I write variance of x? Because what is the definition of variance of x? Summation of xi minus x bar to the power of 2. If I divide it by n minus 1, this is my variance of x. So, but here in the equation, we don't have n divided by n minus 1. We have simply the numerator. So that's why we call it in the denominator, we are going to have SST. Right, so this SST is going to be something that we have here in the denominator, right? So, and then it goes from 1 to n. I can write it like sigma square divided by SSTX. Remember, what was SST? Sum of square of total variation of a variable from its mean. So sum of square total variation of x from its mean, right? Now let's see why this thing is important, has something to do with the variance of beta hat 1. This is also nothing new, right? Because in the assumption number 2, we said that, assumption number 3, we said that we need to have some variability in x, and if you don't have that variability, OLS is going to have hard time pinning down the beta. This is exactly the same here. So let me remind you of that exaggerated example. And I have y, and I have x, and x is only one value, so let's say it's 10. And these are the observations for my y. Now, if I want to use, OLS is going to, kind of, so this is a super exaggerated example. Says that, okay, maybe this is the answer, maybe this is the answer, maybe this is the answer. As long as all these lines are passing through exactly the average, any of them can be the output of the OLS, right? Because what is OLS is doing? OLS is minimizing these distances, the squared version of these distances from the average, right? So which one is it? 1, 2, 3? We don't know. So what does this imply to the variance of beta hat 1? Remember, these are the beta hat 1s. Beta hat 1 here is 0, beta hat 1 here is a negative number, right? So what is the variance of beta hat 1? It's going to increase dramatically. Does that make sense? So this means that if your denominator, if SSTX is 0, the representation SSTX is 0 is exactly this one. There is no variation in x. X is always 10. Then your variance is going to explode. Do you see that visually why it's going to explode? Because for each sample, the variance is going to be one way different a random number. Okay. Then, if I go from this super exaggerated model to less exaggerated model, let's say I have another, well, let me actually go ahead and erase this one. I have another value for x, and maybe we have some observations like this. Then OLS is going to say, you know what, the variance of beta hat 1 is going to be smaller. It's going to be a number close to this one. Now, we get rid of these two models, and then maybe we have this line, this line, this line. Whatever it is, it's a lot closer to beta hat 1, right? To the first one that we were looking into. And so you can see as the variability of x increase, as the variance of x itself increase, what happened to the variance of beta hat j? Variance of beta hat, or beta hat 1, decrease, right? So I write it like this. If this thing increase, SSTX or variance of x increase, the variance of, I'm trying to use different color, the variance of beta hat 1 is going to decrease. So that's a good news. So quickly reviewing these two. The first one, if sigma score increase, we saw that variance increase, so it's a bad thing. Higher sigma score is a bad thing. Higher variance of x is a good thing. And how do I say good thing, bad thing? If the variance of beta hat 1 is a small, I call it good thing. It's a good thing that the variability of your estimated numbers is small, because you're closer and closer to that unobserved through beta 1. And then finally, this is the most intuitive one. This is the easiest one. That's number of observation. So the number of observation, let me use another color for this. Let's use green. What do you think? Without knowing any formula, without knowing any, what does higher number of observation n means? The larger the n, the more data you have. So again, imagine you know nothing about these formulas. Is it a good news that you have more information, more data, or a bad news? Absolutely, it's a good news, right? So the larger the n, the better news for, so I call it good thing. This is a better news for your model in general. So what does it mean? It means that the variance is going to be smaller. The variance of beta hat j is going to be smaller. So I just used that green color here. And it shows here. So if n increase, you know, we are adding a bunch of these positive numbers, because these are all positive numbers. So what does it imply? It means that if your information increase, the summation in the denominator is also going to increase. So it's good news. It's going to decrease your variance of beta hat 1. So these are the three things that your variance of beta hat 1 depends for simple regression model. In next chapter, when we have multiple regression model, we add one extra feature to this variance of beta hat 1. But for now, it depends on three things. I want you to understand the intuition of this variance of beta hat 1 very, very deeply, because it is important. It has huge application. When it comes to hypothesis testing, you know, you have to say it has directly has something to do with the significancy of your coefficients, you know, building, constructing confidence interval for your coefficient, and etc. This is very important. All right. Now that we know what is the variance of beta hat 1, and remember, how was I able to calculate this, come up with the functional form? With assumption number 5 added to the first 4 assumptions. Without assumption number 5, without this one, I cannot calculate this equation. Okay, so this is important. All right. Okay, now that we know what is variance of beta hat 1, let's see if we can literally come up with a number for that. So, because remember guys, at the end of the day, you have one sample from the entire population. I give you one data set from Wooldridge package. At work, you're given one data set. So at the end of the day, your observable things are x and y in one sample. So x can have some numbers, y have some numbers, and all of these things are observable, right? You pass x and y to OLS. OLS is going to give you back beta hat 1, beta hat 0. So these are all observable. Having the beta hat 1s, beta hat 0s, you can also estimate the y hat. So y hat is also observable, right? Having the y hat, you can also estimate the u hat. So these are all, so the observable things are here. These are all the things that are observable. Now look at the equation for variance of beta hat. So is everything there observable? Let's actually work with a less busy picture and formula. So what is observable here? Beta hat 1, one of them is observable. Okay, n, this is sample size. I exactly know what is it. X is observable. I can average it. I can calculate the x bar. This is observable. But what about this one? Remember, what is this? This is the unobserved factor, sigma square. unobserved factor. You know that this is a variance of unobserved factor. So that's an issue. That's a problem. So intuitively it made sense. We know that if in the population the data is noisier, the variance of beta hat 1 is going to be larger. But in practice, I cannot come up with a number. So this is bad news. The bad news is that the numerator is completely unobservable. So what can I do about it? So the answer is, don't give up, just estimate this guy. No, at least in words, it's easy. Put a hat on top of it, right? When I put a hat on top of anything, then I can estimate it. So, but let's see mathematically how can we estimate this thing. How can we estimate the sigma square? And we call it sigma hat. Again, the solution is to come up with the estimated number for sigma square. We call it sigma hat square. And let's open up that the solution. Let's see how we can estimate sigma hat square. All right. So for that, I need to remind you of two terms. One was the error, the other one was residual. Remember, errors are the unobserved factors, right? These are our unobserved things, UIs. And when I say subscript I, it's just for one observation. So u is equal to y minus beta 0 minus beta 1 x1. So where is this coming from? It's coming from our original model. Y is equal to beta 0 plus beta 1 x plus u. So if I solve for u, I get y minus beta 0 minus beta 1 x. And when I put it again, when I put a subscript I, it means that this is for every observation. So I have many of these observations. Observation I, 1, 2 to n. So ui means that, let's say I'm looking at observation number 1. u1 equals y1 minus beta 0 minus beta 1 multiply x1. u2 equals y2 minus beta 0 minus beta 1 and multiply x2 and etc. So that's where the subscript is coming from, right? So this is a reminder for the error term. What was the residual? Residual was the distance, the difference between y minus y hat. How off the model is from the true values, right? Y minus y hat. The y hat is what the model is predicting. Y are the true values. How off you're from the true values. So we are going to say that, do you agree that this is a good estimate for unobserved factor? The answer is yes. We know u's are unobserved. So what is the observable versions of the errors? We call them residual, right? And we were interested in the variance of u, right? So we call it sigma square. What is the best estimate for this guy? The variance of u hat. That's it. We call it sigma hat squared. And I already know what is u hat. This is my u hat. And it is observable, right? Then I'm going to use my, to use the formulas from the statistics to remember what is the variance of x is equal to summation xi minus x bar to the power of 2 divided by n minus 1, right? So let's see if we can come up with the variance of u hat in the same manner. So let's look at that. So the first one basically says that this is the homoscedasticity assumption. The variance of u given x is constant and it's equal to variance of u. So it says that the conditional variance is equal to unconditional variance. So regardless of the value of x, the variance of u is going to be the same, right? And you want to estimate. Let's estimate this number. That's the goal. How do we estimate it? Okay, let's put a hat on top of it and then define something like this. The summation of u hat minus u hat bar to the power of 2 divided by n. Okay, so what is this? I'm not doing anything special here. I'm just simply replacing, look at the equation here, the definition for variance of x. I'm simply replacing x with u hat. So what I have, u hat, this is my x, minus x bar. So what is x bar? U hat bar, right? So this is the variance of x. And if I divide it by n, this is, we are not there yet. So let's see what's wrong with this one. Maybe this is a good estimate for the sigma square, but we are not there yet. So let's read through it. So we say one could estimate the variance of errors, sigma square, this is the one that you're interested, by calculating the variance of residual, sigma hat square, in the sample. Unfortunately, this estimate would be biased. of this. So we are almost there, but not completely there. So this is going to be biased. Why? Because we are not controlling for degrees of freedom. Remember, degrees of freedom are the number of independent observation in the sample. So in a statistic, if I say that this is the definition of variance of x in the sample. So because x bar was already estimated, we say n minus 1. In our econometric here, the unbiased version, the unbiased estimate of our sigma square is going to be sigma hat square, and the degree of freedom is n minus 2. I want you to stare at this equation. Stare at this equation and tell me why an unbiased version is n minus 2. So the degree of freedom is n minus 2. Again, this is the exercise for you. Think about it. I'm going to answer this question in the class as well. Why it is not n? Well, we know it's not n because we are estimating. It has some these values are already estimated. And why it's not n minus 1? Why it is n minus 2? So think about it. However, the takeaway is that an unbiased estimate of the error variance can be obtained by subtracting the number of estimated regression coefficients from the number of observations. Well, again, basically this is the answer. But if you didn't realize that you're literally reading the answer to that question, just think about it more, and then I'll open it up even more in the class. But what is the takeaway? The takeaway from all these things that we talked about is this theorem. We can have an unbiased estimate for sigma square, and that unbiased estimate is going to be sigma hat square. What's the definition of unbiasedness? On average, you're hitting at the target. There's a hat here. I don't know if you guys see it or not, but there's a hat. So the sigma square hat is going to be an unbiased estimate of sigma square. It means that on average, they are going to be the same. And again, looking at the big picture, what are we doing? We are saying that I am interested to see what is the variance of beta hat 1. We got a formula for that. Everything was fine, but the numerator was not observable. So I said, okay, I have to estimate this guy. And now I'm telling you that sigma square, this equation, is the unbiased estimate for your sigma hat square is the unbiased estimator for your sigma square. That's it. Okay, so intuition is important. Whatever I discussed so far, you should know, you have to learn. But calculation, you don't need to do any of these things manually. As we have talked about it so far many times in the course, you don't need to calculate any of these things manually. So actually we're going to use R, and R is going to calculate it for us. So let's see how does R do the job. So again, remember, at the end of the day, I'm interested in the variance of beta hat 1. And if I take the square root of beta hat 1, I get the standard error of beta hat 1. And it's going to be something like this. Instead of sigma, I have sigma hat squared. Unbiased estimate, and divided by SSTX. So now everything is observable. Everything is observable, and R is going to give me back this number at the end of the day. So if you just give X and Y to the R, use one line of code, R is going to give you back beta hat 0, beta hat 1, standard error beta hat 1, standard error beta hat 0. This guy, all of them are the output that you get from a nice table from R. Okay. And so let's see, what do we have on this slide? The estimated standard deviation of the regression coefficient are called standard error. Okay, we call them standard error. Again, this is another subtle things that there's a good chance that I don't know, wherever you learn statistics, you are not paying attention to what's the difference between standard deviation and standard error. And people use these terms interchangeably. So standard deviation is something that we say about the variance, square root of the variance in the population. Standard error, however, is something that we talk about the square root of the variance of, for instance, your estimate in the sample. Because it comes with an estimate, we call it standard error. It's not a standard deviation. But again, people use it interchangeably. Even myself, when I'm presenting my job to the audience, I say standard deviation of the coefficient is this. That's not necessarily right. It's technically standard error. But again, you should know that there's difference between the standard error and standard deviation. And these standard errors measure how precisely the regression coefficients are estimated, right? At the end of the day, the smaller the standard error, the happier you are. It means that you are getting closer and closer to that line that you're looking, population regression function. Hypothetically. All right. Okay, so we are literally plugging sigma hat square for the unknown sigma. Well, this is basically redundant. We don't need this line. We already using the sigma hat square. There is one last thing that we should know, and that's sigma hat itself. So this is our standard error of the unobserved factor. This is the estimated version, right? So this is the estimated version of the standard error for the unobserved factors, and we call it sigma hat. And there's a name for it. In textbook, we use standard error of regression, SER, standard error of regression. It is an estimate. It's a hat version. It's an estimate of the standard deviation in the unobserved observables affecting y. So basically, it's an estimate for standard deviation of your use. It is standard error of regression. They're all the same. All right, so this guy is not observable, but this is observable. All right, so again, conceptually it's clear, but calculation-wise, R is going to do it for us. And most of the statistical packages like R, Python, Stata, whatever, they're going to calculate all these things and give you back a nice table, t-stat, p-values, and etc., right? However, again, in different packages, they call it maybe differently. I don't know why they are not consistent, but whatever it is, in R, it's not called standard error regression. It's called residual standard error. And if you think about it, I think, I agree this terminology better than a standard error of regression, because at the end of the day, this sigma hat is observable, and it has something to do with your residuals. So R calls it residual standard error, but I just want you to be aware, residual standard error regression, they're telling you the same thing. They're all talking about sigma hat square, sigma hat. All right, so that's it. That's the theory part. So let me show you a preview. This is minute 32. So let me show you a preview of how we do all these things in R. And then in the next video, I'm going to review the R file, the R script itself. All right, so let's put it all together. We talked about Gauss-Markov assumptions. These are all Gauss-Markov assumptions. Number 1, linear parameter. Number 2, so this is a very good cheat sheet for your exam, for your midterm number 1. Everything up to the end of chapter 2. Then we have random sampling. Then the variance of x should not be equal to 0, should be a positive number. Then we talked about zero conditional mean assumption, and finally homoscedasticity. With the first 4, we have unbiasedness of OLS, expected value. You see, I'm repeating myself a lot because it is important. So with the first 4 we have unbiasedness, and adding the 5th one, we can say something about the variance of beta hat 1. Even though your exam is open book, but I highly recommend you to memorize this equation for your variance of beta hat 1, because again, application matters. It's not a theory thing. It's very, very applied. When you're doing a research and you're wondering what are the things that are going to, at the end of the day, affect the variability of your estimates. So you have to have a clear understanding in your mind that what are those things, what are these things that the variance depends on. Okay, so don't think that it's formalized theory. I don't need it at work. No, you definitely need it for work. All right, and then so this is the preview that I promised you. So good news is that R is super simple, super simple. So you have to use basically 2 functions, LM summary. So you say, for instance, I want to regress wage on education. How do I do it in R? I say, okay, hey R, I'm using a linear model, LM, And please take this weight as y for me, regress it, use tilde, regress it on education. And R says that, okay, so far so good, but what is the data? So comma, give me the data set, whatever the data. So in Wooldridge, we know that this data is equal to wage 2. This is the name of the data set. And then the close parenthesis, then, so what does this line do? This line is saying that, okay, I take all the wages and all the education. So these are all observable. Behind the scene, I'm going to use OLS. So it means that I'm going to calculate all the beta hats for you. I'm going to calculate the variance of beta hat for you. I'm going to calculate this R square. I'm going to calculate the standard error of regression or residual standard error. And then by this line, I have already calculated this. You are going to say that, oops, wait. Now let's go ahead and give me a summary. So use a summary of it. Summary. This is a function in R. Summary of your whatever it was. So let me call it reg, regression, save it. So call it summary of regression. This is basically how we do it in R in 2 simple lines, or you can make it in 1 line. Summary LM. So here's an example. Summary LM is regressing salary on ROE. And what is the data set? CEO salary 1. Look at the output. So the output, this is an important table, the red one. So we have the estimated number. So this is intercept, beta hat 0, ROE beta hat 1. So these are the numbers. So in chapter 2, you only know these things. And this is a standard error of beta hat 0, standard error of beta hat 1. And these are the topic for chapter 3. And what else? I have residual standard error. This is my sigma hat. And I have R square. We call it multiple R square. So R square. It's only 1.3. And you can use another package called Stargazer and make this table even nicer. So if I do something like this in R, so you have to install Stargazer first. Again, in the next video, I'm going to walk you through this. And this is going to be table. And this is super, super easy and readable. Okay. Again, we have the coefficient themselves, beta hat 1, standard error of beta hat 1, beta hat 0, standard error of beta hat 0, number of observation, and R square, adjusted R square, something that we cover later on, sigma hat, and then this is something that we cover later on, this is something that we cover later on. So that's it, that simple. All right, so let's stop the video, see you in the next one.